the Sustainability Management Master's Program, you're answering one simple question. Do you care about your future generation? If you care about your kids, their grandkids, then you care about sustainability. And a sustainability manager is someone who has the tools to make people understand how they can contribute towards developing a sustainable world. We have both part-time and full-time students. Our curriculum is 30 hours. Instead of thesis, we have a research project course and a seminar course which provides them with the kind of research background they will need to be successful in their job. But at the same time, sustainability is not always everything about environment. It also relates to the business. They will take a sustainable business strategies course. They will take a project management course. Most of these courses are going to be taught by industry people, the people who are doing sustainability on a daily basis as a part of their job. Any organization that has a large number of employees and has a physical infrastructure, they will have to have a sustainability office. If you have the passion to develop and maintain a sustainable world, come to us and we will help you shape your passion into a career which will create an impact.
The Stevens Institute of Technology is proud to present the Hugo New Corporation Sustainability Seminar Series, co-sponsored by Geosyntic Consultants, H2M Architect Engineers, Brown & Codwell, and BEM Systems.
Yeah, thanks, Dibs. Thanks for inviting us to be here, and we're happy to give a presentation. We've put together some thoughts and some materials which hopefully you find interesting and practical. Geosyntek is a sponsor, as is shown there. We don't have any slides on Geosyntek. We've kind of gone straight into the technical discussion, but if you're interested in learning more, definitely reach out to us. We have some slides, as you may have heard from our introduction. We do a lot of sediment remediation work, a lot of dredging design and oversight. And so given the area where we are here in the New York, New Jersey harbor estuary, we thought it'd be good to talk a little bit about this today and how sustainability can be roped into that, that market. So we have maybe 30 slides or so, but a lot of pictures. You know, it's Wednesday afternoon at 5 o'clock, so we tried to put a lot of pictures in here. And we don't have a lot of equations. I don't think we have any equations. So we're going to talk about dredging and these dredging projects that occur in the region. There's two different reasons that people do dredging. The first one is navigational dredging, the second is environmental. Navigational dredging is the maintenance of channels for commercial and recreational vehicles, basically maintaining that pathway into the port or into through the waterways so that goods can be transferred. So sediment in the water, you know, moves all around, it silts in, and you have to maintain those channels. So there's dredging operations in the major ports, in the major waterways throughout the year just to maintain these active channels. And they're usually federal, state, or sometimes private projects. If it's, you know, even just a small marina who's got boats, they want to make a pathway for their boats, for their vessels. And that's, you know, a lot of Army Corps projects are the navigational dredging, but environmental dredging is a little different. That's regulated by federal and state agencies where there's contaminants, and we need to improve the environmental health of the system. And so we're going in and removing sediments to get rid of those contaminants, and we're taking them off somewhere else. We work mostly on the environmental dredging side of things, working with contaminants. But it's basically the same process, just what happens with that dredged material afterwards is really where the distinction is. So looking at the navigational dredging for New York and New Jersey, the port of New York and New Jersey, I think it's the third most busiest or third most active port in the United States and the most active port on the eastern seaboard. So there's a lot of dredging, a lot of maintenance of the channels in this area. So about 3 to 5 million cubic yards of dredged material are removed annually. And that material, given the fact of this industrial waterway, you can see it in the photo, there's a lot of background contamination from urban sources, just runoff from stormwater and other, you know, historical industrial operations. So this is just a plot of PAHs within the harbor dredged material. And You don't have to take too much from it, other than the fact that there are PAHs in the sediment, and sometimes those have to be managed accordingly. Whatever you want to do with that material afterwards needs to fit some criteria for the end use, and sometimes the PAHs or other contaminants might restrict that. So we might need a way to manage that. So that's navigational dredging in this region. I'm not sure if we can see Stevens in that photo, but probably could if we look close enough. This is a slide focusing on more of the environmental dredging projects in the area. Some of the big ones you could see, we'll start kind of at, say, like 11 o'clock over here with Lower Passaic River. That's one of the bigger ones. That project is, I think it's, I'll have to look it up, but I had all the notes right here because there's a lot of money and a lot of volume. Passaic is 3.5 million cubic yards of material that's going to come out bank-to-bank dredging, and it represents about $1.5 billion of work. So that is just to clean up from the dioxins and all the historical use over there. Another project, and you can see that feeds into Newark Bay. Another project that's underway on the lower right is the Gowanus Canal. That's about 590,000 cubic yards, not as big as Passaic, but still about $500 million, $500 million of cleanup. Berries Creek at the top there, that's a little smaller. I'll try to point it out. It's this little, these tributaries here. There's a lot of mercury up there. That's, I think, some of the highest mercury concentrations in the US and maybe in the world in the sediment. But that site is, I think it's like about 330,000 cubic yards, a good $300,000. And those are the projects that we know right now are happening. Newark Bay is under the investigation phase. That's going to be a major dredging. Hackensack River is going to be likely listed as a Superfund site too soon. And then Newtown Creek over in between Brooklyn and Queens, that's another major site. It's probably going to be another $1 billion worth of cleanup. So the point here is just within this region, we're looking at, I don't know, a couple billions of dollars worth of cleanup, millions and millions of cubic yards of sediment that needs to get managed properly. And typically what happens is it goes to a landfill and it gets disposed of and covered. But maybe there's a way that we could use this material for our benefit and you know, think about sustainability. What's the best way to use it, and can we use it as a resource? So that's pretty much this slide. What do we typically do with this material? So in the past, there's been these CAD, that's a confined disposal facility or confined aquatic disposal. So disposing of the material, dredging it up from here, placing it over there, and then capping it and sealing it off. That isn't used as much anymore, and in locations where that is used, the capacity is filling up. So we're running out of space for that. Same with ocean disposal. There's some ocean disposal that still occurs, but it's not as common. Direct landfill placement is something that's used more often, is to just take it to a landfill, and that's, you know, capped and put away. And you can see in the photo that's using the material as a daily cover or daily pre-cover. So that's where the material is dried out, the sediment material is dried out, and we put it on the landfill to cover it up at the end of the day. And then you come back the next day and they get back to work. A couple of the other options, which are more on the sustainable front, is mine reclamation and brownfield redevelopment. We've certainly worked on projects where dredged material, typically navigational dredged material, which is cleaner, it gets used to redevelop brownfield sites or sites that are contaminated that they're trying to redevelop. And so what they can do is a lot of times raise the grade, especially now with sea level rise being a concern and coastal areas being a concern. They want to raise the grade where there's intersection with the sea and the waterways, and so they want a source of material, a source of fill, a source of dirt. And so this is a source that we showed. Millions of cubic yards are dredged annually. It's kind of a supply and demand type thing here. So this is what's typically been done, but the brownfield redevelopment is tricky because you have to line up when the material is available with when the site needs the material. So you need to have it work out just right. So like we said, landfill placement's typically been the most common approach, but why are we looking at alternatives? Why do we think that there's better ways to do this? Well, number one, the remediation will cost to the responsible parties. So looking at environmental dredging, I mentioned that there's billions of dollars being spent. The majority of the cost of those billions of dollars is the management of the sediment. It's not necessarily getting the equipment out there to dredge it or to do some of the other work around the site. It's really just how do we get rid of this stuff? That's where you spend the most amount of money. Probably a third to a half of the cost of all these projects is just getting rid of the material. So we want to cut the cost of that to the responsible parties and to the public to the extent that they're paying for it. So finding a more sustainable, better approach to manage this material certainly pays off in dollars. I mentioned earlier about the CDFs and the CAD facilities. The capacity is filling up, and so we don't have the same locations to put these in anymore. It's filling up. I know I think it's in Lake Erie, there are CDF facilities filling up, and they're going through a beneficial use management plan right now, trying to figure out how best to use the sediment that they need to dredge up in the Great Lakes. Yeah, I think we'll go to this last bullet, greater understanding of sustainability factors. This sustainability is becoming a larger trend. There's both in terms of the transport of material to the end-use locations, but also some initiatives such as New York's Zero Waste to Landfills initiative, which has ambitiously sought out to reduce any deposition of material to landfills by 2030. So this applies not only to dredged material, but also their biosolids too, from their water treatment facilities. So if we can find some beneficial use for the sediments and the biosolids, that fits in with their initiative and meets their goals. So there's several driving forces to landfills. And so I've used the term beneficial use a few times. This has been a major focus area in sediments, and sediment management, probably for a good 20 years or so, but it's really starting to ramp up now, given the factors that we just mentioned. So there's a few panels that have come together. This is from CETA, the Central Dredging Association, and they've defined beneficial use, and you can see that there. But they've looked at 5 R's, as they've called them, in terms of how best to use dredged material. And they've looked at it from raw material, incorporating dredged sediment material into raw material such as bricks and things like that. Looking at remediation of cleanup sites, maybe taking that dredged material, processing it, and using it as clean fill. Reclamation, expanding existing land. But we've highlighted the last two, the restoration and resiliency. Those are in red, obviously. Those have really come on in the last few years and are opportunities for this material that wasn't necessarily as much of an emphasis as it is now, given the climate change and the hurricanes that have come through. There's more projects looking at restoration and resiliency. So in terms of matching up that supply and demand, that demand is growing for fill, the demand is growing and the supply is still here, so maybe we can connect the two. Another angle here is in terms of emphasis on the waterfront and sustainability. There's been some growing attention on waterfront design guidelines. This is a program that's been sponsored by the Waterfront Alliance in New York City, where they've come out with design guidelines for the waterfronts and assigning point system to how well you can incorporate ecology and resiliency into the waterfront design and waterfront development. And as you can see on the right there, one of the credits is to use sustainable fill and soil management, and this covers beneficial use of dredged material. So if we can bring dredged material into these projects, there's a credit for them. And then you can get certified as a waterfront edge design guideline. I don't know what they call it, but you get certified as being responsibly developing the waterfront. So this was launched in 2015. This is a New York City-based organization, Waterfront Alliance. They've got a sister organization in Philadelphia, and I think they're looking to make it go nationwide. So there's definitely more attention being placed on this. So I'm just going to walk through a few slides on just dredged material management, what happens to this material after you dig it up, And then Russ is going to talk more about, from the sustainability side, can we do some quantitative evaluations of what the benefit is from a sustainability perspective. So I think that's why you're all here. So we'll try to get to that a little quicker. So what happens after you dredge the material up? It's relatively straightforward. So the first thing you need to do is to screen out some debris, and that's what the photo shows here. The larger photo is you have this bucket of material, you pass it through a screen, and you might be able to see there's some tires coming down that chute. So the material falls through the screen, but the larger material gets retained. As you can imagine, in a lot of these industrial waterways that have been active for 100 and 150 years, there's a lot of large debris out there, a lot of metal, concrete, bulkhead pieces, timber, tires, and all of this kind of interferes with how we're going to manage the sediments. We need to separate that out first. There's also some archaeological considerations where some people in the community may be interested in what's in the waterway from a historical perspective. And there's also not just community, but actual historians who are interested in this. And so you have to employ some archaeological colleagues to take a look at the material that comes out and say, yes, this is of significance, or it's not of significance. And on the bottom are just some photos of cleaned up debris, which gets pulled out of some New York City waterways. So the next step, once we get the debris out, is to try to stabilize or solidify the contaminants. And this typically refers to the use of Portland cement to add it to the sediment, mix it up, and do two things. Number one, it's going to bind a lot of the components, such as metals. It's going to be bound right into that matrix. Or you can entrap the contaminants within that, and that's more with the organics. And the end goal here is to make this a safe material, something that can be transported and placed at the end use disposal. So when you're looking at leaching from the sediments, you're binding everything up in terms of the metals and the organics. It's also a way to dewater the sediment as well, so you can transport it properly. So looking at some of these facilities that do the processing, which is the Portland Cement Edition, there's a number here in the New York, New Jersey area, which is shown on the map on the left, which is a little bit dated now, but the idea is the same, that there's facilities out there that are managing this, and commercially viable facilities that accept dredged material for their living, and they manage it and process it. And on the right, that's the Clean Earth facility in Claremont, which is where a lot of environmental material goes. So if we're dredging in the area, we can just take it across the harbor over to one of these facilities, and if there's an opportunity to use this material locally, it's not like we're going very far away. It's right here. Here's a few options. This is a table that we put together in terms of how best to manage the material, and we're not going to go through all of these in detail. We've got pictures coming up of each of these, but in general, there's a few ways to process the sediments to render them safe for the next use, whether that be going to a landfill or some sort of beneficial use. And I'll stress that even when you take it to a landfill, there's acceptance criteria that needs to be met. So chemical acceptance criteria, physical acceptance criteria. You can't just send them anything. They need to test it and make sure it meets whatever their permits say they can take. In order to do that, sometimes you need to process it or treat it. And here's a few options. There's low temperature thermal desorption, which is applying heat to volatilize some contaminants off of the sediments. This is applicable to whatever's volatile. Petroleum hydrocarbons are the best. Relatively high cost because there's a fair amount of energy going into that. But you do get a clean end product, which comes out of it because everything's sort of baked off of it. But one of the issues here is the dewatering. Because if you have a lot of water in there, obviously that's going to take the energy of the heat instead of the volatilization from the contaminants. The water is just going to soak it up and you're going to evaporate the water. So you could go to high temperature thermal desorption, which works a little better for some of the less volatile contaminants like PCBs and pesticides, maybe even some metals. So this works even a little bit better, but of course it's probably more expensive. Soil washing has been done in the past. That's, as you would think, just kind of applying surfactants or some soap, if you will, to the soil, mixing it up, trying to pull out and partition out the contaminants, the organic contaminants in this case, from the soil. This needs a fair amount of infrastructure, a large footprint. It's not great for fine-grained material because, as you can imagine, there's a lot of surface area of fine-grained material. You got to mix it up a lot more. So it's not used too often, and again, the cost is pretty high. Say mechanical dewatering is used pretty regularly. That's where you're just basically squeezing out the water from the solids. And this is used a lot just to manage the amount of material that if you were to add Portland cement to it, you don't want to add so much that it's just soaking up the water. You want to add it, you want to limit the amount of water in that material, so when you're adding the cement, it's binding it up, and it's not just binding up the water. Then there's some alternative amendments, which we were just talking to Dibs about a little bit ago, in mixing in some things like alum, aluminum hydroxides, and others for more specialty type of applications. We have the relative cost being low, and it's versatile, but depending on what you want and what you need, those could be available. So the point here is there's a lot of options, a lot of things that we could do to render the material suitable for the next step. We've just got a few pictures of what this looks like, and you can see that this is the desorption facility. It's pretty large footprint, a lot of process engineering involved. But you can see there's a dryer and roaster in the middle of all of this, which is in the orange there. And basically you're adding the material to that, drying it out, and then at the end you've got clean soil, which looks really nice. Soil washing, again, is a large footprint here. A lot of infrastructure to wash the material. And usually there's economies of scale, so the bigger you have these things, the more you're going to get out of it. So you do want to have some large facilities. Belt filter press and plate and frame, these are dewatering approaches. So on the left is the belt filter press where you're squeezing the water out, and you're hoping with that poor water comes contaminants, and you have more of a dried cake at the end, which is more workable than the plate and frame on the right. This will be my last slide. I'll turn it over to Russ, but this is just a chart of some of the projects that were accepting dredged material. This is back in 2013 time frame, so it is a little dated, but the point here is you kind of look at it. There's a lot of projects to match up the use or the dredged material with the end use. And you can see that there's a number of landfills, there's mines, some golf courses get used. If you're out at a golf course and you see all these hills, a lot of that might be from dredged material because it's cheap and people, it's available. But what's been coming on more in the last few years on the right is the opportunities with resiliency projects. A lot of resiliency projects are being designed right now, and they're probably going to be constructed. I know there's been several of them already constructed. There's the Battery Park City Resiliency, East Side Coastal Resiliency Project in Manhattan, Lower Manhattan Coastal, and there's a few others there. But all of these projects are looking at raising the level of the grade, raising the elevation to protect against floods and storm surges. In order to raise that grade, we need material. And dredged material is a good source of that, and is there a way to render it safe, and is it a sustainable approach? And so that's where we have come in and started to take a look at this. And Russ, I'm going to turn it over to you. You want to go? You want me to do this one? Okay, I'll do this one. This is I'll do. I can't do all of them. That's the thing. So this is the East Side Coastal Resiliency Project. This is Lower East Side of Manhattan. The green is, I guess, where they're looking to. I guess that's the park, and they're looking to build it out. I think de Blasio had put out something not too long ago where they wanted to build out into the East River by 50 feet, and they want to put in a new park. But basically, this is to protect the Lower East Side from storm surges. So they're putting in a raised bulkhead. They're putting in, going out into the land, raising the elevation. And you can see there up in the top left, they want to basically bury the park now with 8 to 10 feet of fill. They're going to put some park over the top of it too. It's not just burying it and letting it go. But that's a lot of material when you start looking at it. It's a large volume of material. you know, there's dredging projects happening right down the river. Why don't we just dredge it and bring it over here? And that's kind of a great supply and demand story. So this is just one example. There's all sorts of other projects in the works, but in Jersey City, in Hoboken, and in New York City. So if we can try to match some of these up, it's a great opportunity, and we don't put as much material into landfills. All right, I'm going to transition here.
Thank you. Do you expect any other metals like the mercury in these sediments?
Certainly. Yeah, I'm not on the mic anymore, but you guys can hear me. The one site in New Jersey has got very high mercury, the Berry Creek site. And yeah, there's just background levels all throughout New York, New Jersey waterways from the industrial history. And I mean, I'm sure you're aware, but in the past there wasn't such strict environmental controls on disposing of wastes. So a lot of the waste just got dumped into the waterways, and that was how it was. But those legacy contaminants are still there. They bind to the sediments, they don't go away. And so there's a pretty fair amount of background contamination in the New York, New Jersey area. So even when there's navigational dredging, it's got mercury in it, arsenic, metals. But some of the sites where there's more of an environmental issue, more of an acute issue, that's the concentrations are, you know, an order of magnitude greater. So.
Thanks. So Dave was talking about, you know, one of the alternative methods we have for using this dredged material instead of stressing our landfills and doing the more traditional beneficial use applications. And so he was talking about the resiliency projects is a great idea. The other idea that we're floating around right now is, what about taking that dredged material from these environmental projects and putting it back into the same waterway? So it's a little bit of an outside the box thinking idea. And the questions, you know, that we have to ask ourselves is, as engineers, is one is, you know, are there measurable benefits here? Is it even worth doing it? And then two, is it safe? You know, are we going to potentially be leaching out the material back into the waterway and just effectively not doing what we're hired to do here? So just to give you guys kind of a background here, this is what, you know, a traditional remedy approach would be. You know, so you have your waterway, you have your soft sediment on the top there, your recently deposited material, and then underneath that you have your native sediment. Typically they're both contaminated, and what you'll do is you'll remove that soft sediment layer, you'll leave that native sediment there, and then you make a nice level area and you put down your cap. Now this cap is a reactive cap. It's a reactive treatment layer, or there will be reactive treatment layers in it. And so any contaminants in that native sediment that we didn't dredge out, it's going to, that cap is going to sequester anything and prevent any sort of anything from getting out into the waterway. So our idea is, what if after we dredge that material, we process that dredged material, perhaps even on site, so not even going across the harbor, doing it on site, and then putting that material, processed dredged material, back into the canal or into the waterway in some areas where you can. I mean, obviously in some areas you can't do this because of navigational reasons. You don't want to put, you know, increase the elevation here. But in areas where you can, put it back in, then put your cap on top of that, and then you put clean fill up and you can have yourself a wetland. So, you know, some of the benefits to this approach, I mean, this is kind of a list, you know, as sustainability practitioners, I guess you can think of the three-circle Venn diagram with the social, economic, and environmental, and in the middle is sustainability, right? So, you know, here's some of the more qualitative things that are the qualitative benefits. You know, one is the community is, in these sites, they typically want to see, okay, you cleaned up the waterway, but now let's get access to it. You know, let's put a park there. Let's make it something that the community could use. And so, you know, doing something like this, you're going to be integrating the community vision into your design. So of course you're going to have greater social and ecological value. You have you're building yourself a wetlands here, and you're incorporating elements of climate resiliency into the design. So you're creating a buffer for flooding by putting these wetlands in. And of course, you're reducing that stress on the landfills of bringing this material over to a landfill, either for daily cover or for direct disposal. And last but not least, you could be saving some money in your construction costs. So one of the more quantitative ways to do this, and I don't know if you folks have ever played around with this, this is Sitewise. It was put together by Battelle, a collaboration of Battelle, U.S. Navy, U.S. Army, and Army Corps of Engineers. And what you do for this is basically it calculates your environmental footprint for different remedial alternatives. And you can use this to get a quantitative assessment on greenhouse gas emissions, energy usage, air pollutant emissions, water usage, and even accident risk. So what we use this tool for in this analysis that we did for this one particular site is just kind of a quick, let's get some ballpark numbers here, right? Let's put in what our scenario is, or what our different remedial alternatives are, and get a sense of what maybe the numbers look like. Then if this looks good, maybe we dive in a little bit deeper and do a real in-depth greenhouse gas emissions analysis where you do the scope 1, scope 2, scope 3 emissions. So we compared these two different alternatives. The first one, alternative 0, I named it, is placement of the stabilized dredged material at your landfill as daily cover. So in that instance, you got your dredge bucket, you drop it into a barge, you transport that barge to one of those processing facilities that Dave has showed. You add your Portland cement or whatever your additive is, stockpile, let it cure. Then you're going to load trucks and truck it out to whatever landfill you are using for daily cover. That's one option. Now, and that's the more traditional beneficial use option. The other option here below is what we're proposing. What if you just dredged it, put it in a barge, added Portland cement or whatever your additive may be in that barge, take that material and place it back into the waterway in some areas. So we ran the numbers and they look pretty good. This back of the envelope calculation is pretty promising, and we used 210,000 cubic yards of dredged material for this particular site. That was the amount of material we were looking at. And we were getting a 31% reduction in total energy used, 7% reduction in greenhouse gas emissions. That's not great. It's okay though. And again, I would be curious if when we jumped into scope 1, 2, 3, what that number would look like. And then for PM10 emissions, 238% reduction, and that's mostly due to all those trucks that we just eliminated from the road. So the question of is it worth it? It seems to be like the initial investigation is saying yes, we should do some further evaluating here. This makes sense. And the other question that I brought up is, it's safe. What we did, what we want to do is look at the leachability. And so for leachability, what we want to look is the long-term leaching potential. And we want to do a test where you mimic the waterway conditions. So David mentioned that when you bring this material over to a landfill, you have to do waste characterization testing. And as part of that, you'll do what's T-clip testing, toxicity characteristic leaching potential. Yeah, okay. So that's a pretty traditional test. And really it's basically done so you can prove that your material isn't a characteristic hazardous waste, as RCRA says. And then you have this other testing, SPLP testing, that is really meant for what are the conditions at the landfill. So it's as if you have a leachate running through the substrate, and so it's a little acidic, and what's going to happen to the leaching potential from that leachate when that leachate goes through. So these methods are great, but they're not exactly perfect for our application putting the material back into a waterway. And it doesn't really mimic the waterway conditions. So there's usually a lot of data for that, because that's really in your kind of traditional testing, sampling program and analysis program. You'll have SPLP and T-clip data. So we have sites where we have tons of SPLP and T-clip data, but it's not really that useful for this application. What we really are after is another EPA method, EPA 1316, which is actually, we're modifying that method to using a neutral pH. And there's usually very limited data for this. It's just not a requirement for upland placement, so you don't run the test typically. And what we also want to do is we want to run that test, so you can take a sample, you'll do benchmark testing, you put it in a mold, and you'll want to do it, run the test 2 hours, and then 2 days, and then 6 days, and then maybe even a year after, just to see what that kind of long-term leaching potential is. So that's kind of the approach that we're looking to take. And at this one particular site, we're showing you some data here for. We found very limited data, but the limited data that we found tells a pretty good story, because what it tells you is, so that blue is the untreated native sediment. And over here you have your cumulative pH release, so your mass release. And the orange is the treated material. And so what this is saying is that the untreated native sediment that is usually underneath, that you're not dredging, and you put the cap on top of, that actually has more leaching potential than that processed dredge material. So if you put processed dredge material on top of that native material, and you designed a cap to be able to sequester all of those contaminants from the native sediment, then it should be able to handle the processed dredge material, which has a lesser potential for leaching. So it's telling a pretty good story there. I'll go back. But again, this is very limited data, and really all it's saying is it's worth looking into. Maybe we should look more into it. We should do some more treatability studies and really see what's going on here. So moving away from sort of the technical realm and getting into more the regulatory realm is these are some new ideas. We're going beyond what's typically done for beneficial use of dredge material, both what Dave was talking about with using it for these resiliency jobs, and with doing this idea of putting it, using it for on-site wetlands restoration. And so the regs are not really designed for that. And so, I put this slide together just basically to say a few good things and bad things. One, New Jersey is great. I mean, a lot of the other states, New Jersey has a pretty advanced sort of environmental protection department, and a lot of other states look to New Jersey for guidance. And one thing that they did, they centralized their dredge management area and into the Office of Dredging and Sediment Technology. So it's great. You call those guys and they can help you. It makes our lives as consultants a lot easier. But we would like to see more of that, making it one single department to go to. The other thing, moving to the second bullet here, is just develop legislation that really promotes beneficial use, which this is already out there. In fact, New Jersey mandates beneficial use whenever dredging is undertaken. But again, this is the more traditional beneficial use. I mean, they're counting bringing it to a landfill as daily cover as beneficial use. So, we'd like to see more legislation that is really promoting these other ideas of beneficial use. And one of the barriers I point out is a lot of these, if you want to use a material as fill material, a lot of the standards will give you concentrations in bulk sediment or bulk soil concentrations. And so it'll say if you're at 80 ppm or ppb of benzoate pyrene equivalent, for instance, you cannot use this material here. Even if you can show them, hey, yes, the contaminants are there, but there's no potential for leaching, the regulations are set up so that you won't be accepted to do that. So if we can maybe develop some smarter regulations of what to do with this fill material, and really think about, not just put in a number and think about, what that number is based off of. it would also be helpful. Now there are already a lot of green. I'll just go through this really quickly, but I just put this slide together to show that there's a lot of green initiatives going on in the environmental, both at the federal, state, and local level departments. I mean, EPA has a clean and green policy, and basically there's the idea of green and sustainable remediation practice is really a growing trend, and the regulators are on it and they're looking at it. And so, they're coming out with guidelines now of, of what to consider from that perspective while you are looking at your remedial alternatives. So that's good and that's promising. We want to see more of that. So just to summarize here, I mean, there's right now, and so Dave and I, we do a lot with this dredging projects. And there is a ton of discussion in this industry about beneficial use of contaminated dredge material. I think it's next week or a week after, we're going to a conference in Wilmington, Delaware, that they're just going to be talking about beneficial use of dredge material. And that's through WEDA, the Western Dredging Association, which is one of the biggest associations out there regarding dredging. So there's a lot of buzz around beneficial use and alternative methods for beneficial use. The other thing, the take home here is you can't just do it on your own. Getting these nonprofits and like the Waterfront Alliance and these WEDGE, their guideline that they came out with that Dave mentioned, get those guys involved. Everybody needs to be at the table for this. And there's this natural connection now between dredging projects and coastal resiliency projects, which this is a developing thing. This is new, and it seems like a good marriage. So the last bullet is just now is the time to think innovatively, and hopefully that something came out of this presentation that may have spurred some imagination or some discussion at least, and we've got to get creative now, and so this is kind of one of those ideas that we want to present to you guys. I think with that we've ended our discussion.